So thank you very much for organizing this. It's really a lot of fun to be here. Thanks a lot for having me and letting me talk about some joint work with Andrei Kuparsky, actually, who's in Grenoble and also, I think, affiliated with Moscow. So those of you who have been like overwhelmed as me with tropical geometry during the past days, now you can really relax because we're going back to Euclidean geometry. So vertices, facets, half spaces, everything is as it is. Polytopes are as they are. And actually, I will talk about a very particular family of polytopes, which I like a lot. And I mean, I think they were mentioned on Monday already, which is the family of two-level polytopes. So two-level polytopes, that's a very simple concept. They satisfy the following property. So for every hyperplane that defines a facet of the polytope, you want that there is one second hyperplane, which is just a parallel translate of that hyperplane, so that all the vertices are contained in these both facets, okay? Or in other words, all the vertices that are not already in that facet, they can be covered by a single parallel shift of that facet. That's a two-level polytope, okay? So here are some three-dimensional examples, right? I think the simplest one is maybe the cube, right? So that's fine. We have a cross polytope over here, which is also two-level, right? This one is also two-level, okay? This one is not two-level. I mean, this top facet is fine, right? You can cover everything by two translates. But if you look at that facet here, right? I mean, you need one translate to cover these four guys, but you need another translate to cover these two guys, okay? So this is not two-level, okay? Daniel.
Yeah, why is the cross?
At least if you draw it in the right way. I mean, it's like, if it's really regular, right? Like this, take this facet. I mean, every facet is the same as this one, right? You cover these three guys, and with one shift, I mean, put it.
But is that only in two? Or
No, it's in every dimension. It's really, yes. So this is easy. Right, so this is three-dimensional example. So let's go to higher dimensions. Actually, in higher dimensions, there exist many very interesting two-level polytopes. So I guess it's clear that hypercubes are two-level. Actually, as you just asked, cross polytopes are also two-level, and it's easy to see. Okay. Simplices, every simplex is two-level. It's also easy. But there are some more interesting polytopes from, combinatorial optimization, for instance. So for instance, matching polytopes of bipartite graphs or Birkhoff polytopes, they are two-level. If you know what an order polytope of a partially ordered set is, they are two-level. My favorite two-level polytopes are stable set polytopes of perfect graphs. We will see that in a minute, okay? Stable matching polytopes, if you know that, they are two-level, and several other polytope, Hansen polytopes, whatever. Okay, so let's get a rough idea why is it true that maybe stable set polytopes of perfect graphs are two-level? That's actually very easy, okay? So what is the stable set polytope? You take an undirected graph. Now what's the vertices of that polytope? You take every stable set in that graph, you look at the characteristic vector, and then you take the convex hull. That's the stable set polytope or independent set polytope, okay? And then for perfect, I mean, in general, it's very hard to describe stable set polytopes, but for perfect graphs, those are exactly the graphs for which we have such a nice description, which is due to Schwartal. And the description is as follows. You write down some non-negativity constraints. Okay, that's what you always do. And then you write down a constraint for every click in the graph. For every click in the graph, you basically say that, every stable set should intersect in at most one vertex with that clique, okay? And that's what the inequality is saying. Good. So why is that two-level? Well, that's easy. I mean, let's look at facets that come from the clique inequalities, right? I mean, look at the left-hand side. So if you plug in a vertex, there are exactly two possibilities. Either you're on that facet, which means that the left-hand side is exactly 1, or the left-hand side is 0, okay? And so this gives you exactly the two hyperplanes, right? Sum is equal to 1 and sum is equal to 0. Okay, was there a question? No, okay, great. Good. All right. So why are we interested in these polytopes? Let's start with some very simple facts, and then let's get to the more interesting facts. So this is something that, so the first two facts are very basic, and this is something that I would like to remember. Okay, we will need this in a minute. So first of all, it's easy to show. That's a nice exercise. Every two-level polytope is actually a finely isomorphic to a 0-1 polytope. Not vice versa. Not every 0-1 polytope is two-level, but two-level polytopes are essentially 0-1 polytopes. And the second thing, also a simple exercise, is if you take an appropriate dual of your two-level polytope, it's also two-level. Okay, good, good. Now, the reason why many of us have been or are interested in two-level polytopes is that they have very small semi-definite extended formulations. So if you don't know what that means, it means, or here's a precise statement about this, every d-dimensional two-level polytope is an affine projection of a slice of the cone of symmetric positive semi-definite matrices of a very small size. So they are d+1 times d+1 matrices. Okay, so it's a cone of a quite low dimension. So why is this remarkable? So what you do is, I mean, if you have this, then this means that if you want to optimize over a two-level polytope, a linear objective, you can equivalently write down a very small SDP. Okay, and we are happy because we can almost solve them, right, efficiently. And this is, by the way, this is the only reason why we can solve the weighted stable set problem in perfect graphs. Okay, there is no combinatorial algorithm known for that problem. So this is a very well-known fact that you should definitely know. Okay, now people from the field of extended formulations, they were wondering about, I mean, can we also do the same with linear extended formulations? Okay, instead of semi-definite ones. And actually, we don't really know. So there are lots of open questions about this. So one main question is, given a two-level polytope, can I have at least a sub-exponential linear extended formulation, okay, for such polytopes? And the answer is true. The answer is yes for several examples. So one very prominent example is, again, for stable set polytopes of perfect graphs. So that's really, it's non-trivial to get such an extended formulation. And this is a construction by Yanakakis. It's not obvious at all. For all the other examples that we have seen, that's trivial because they have just a small number of facets. But in general, we don't know. And there is a nice connection to a very famous conjecture in communication complexity due to Lovash and Sachs, which is the so-called log rank conjecture. If you're interested in, I can tell you afterwards what it says. So it's a conjecture, so it's open, okay? But if the conjecture is true, then it turns out that every two-level polytope will have a quasi-polynomial size extended formulation. And we have no idea how to construct it, okay? And this was one reason why at least several people in the field of extended formulation got very interested in this, because during the past years, we have learned how to prove strong lower bounds, okay, on sizes of extended formulations. So maybe one thing would be, I mean, take some two-level polytopes and prove very strong lower bounds, because this would give implications for the log rank conjecture. I mean, you could refute them possibly. You could refute the log rank conjecture, okay? But so far we haven't been very successful. I mean, we tried a lot of things, or people tried a lot of things. So as you see, I mean, many people studied, I mean, recently studied two-level polytopes. So you see several familiar names from extended formulations. You see several people that we have seen this week, Raman, Sanyal, but also people like Parillo or Rebecca Thomas and so on were very interested in two-level polytopes, okay? So I hope I could convince you that, you know, these two-level polytopes are interesting objects. All right. Yes. I think so. It is a two-level polytope.
It is.
Yes.
Sorry, what is the lower bound that Fiorini has used?
This is for the correlation polytope. Oh, no, correlation. No, unfortunately not. It's like, I mean, I have showed you several examples, but it's still a very special property. So most other polytopes we know are not two-level. So that doesn't help, yeah. Yes, exactly. Good. So let's look at one of these studies here by some more extended formulations people. So here's a question to you. So what is the largest number of vertices that a d-dimensional two-level polytope can have? What's your guess? 2 to the d. Okay, why? Well, they are essentially 0, 1 polytopes. That's one reason, right? Good. So this is 2 to the d. The same holds for the number of facets. I mean, you can. I told you that you can dualize things, so the same should hold for facets. And you know, we have also seen examples that this is tight. Okay, this is tight. The first one is obtained by the hypercube, and the second by the cross polytope. Good. Bohn, Faenza, Fiorini, Fisikopoulos, Macchia, and Pashkovich, they have studied two-level polytopes quite a lot. They have looked at them from all the sides, how to construct two-level polytopes, how to characterize them, whatever. Counting two-level polytopes is very important to maybe get some lower bounds and so on. So they did lots of studies and moreover also lots of computational experiments. And one thing that they observed is that, okay, a two-level polytope, it can have many vertices, it can have many facets, but if you look at these extreme examples, it seems that you cannot have many facets and vertices simultaneously. And this is also like the thing that they observed, at least in their experiments. I mean, is it possible to have many facets and vertices simultaneously? And one thing that they did is they made a very nice plot of these, the number of facets and vertices, okay? And you see that, I mean, it was really like one thing that was really obvious was this very nice curve that they drew through their plot, okay? And then the extremes, like the extremes here, if you want to have many facets, I mean, that's the cross polytope. Here you have the hypercube, and there's nothing far from that. And then you have that curve. And based on that plot in their experiments, they put up a very nice, I think, a very nice conjecture, which is this one, okay? So that's the conjecture, which says that for every d-dimensional polytope, that's one way to quantify, you know, trade-off between vertices and facets. Maybe the product of the number of vertices and the number of facets is bounded by d times 2 to the d plus 1, which somehow means that you cannot have both like exponential at the same time in some sense. Okay, good. They were also able to show with very extensive computational experiments that this conjecture is true up to dimension 8. Okay, and this is really not easy. I mean, you have to work a lot until you get there. Good. Recently afterwards, Manuel, Alfonso, and Yuri, they were able to prove that this conjecture is true for many interesting polytopes. And they were able to prove that it's true for all the polytopes that I've previously mentioned, like order polytopes, Birkhoff polytopes, stable set polytopes of perfect graphs, and so on. So for those polytopes, the conjecture holds true. And our result now is that it holds true for all polytopes. So this conjecture is true. So in the remaining minutes, I would like to give you some idea how we proved this. So when I saw this conjecture for the first time, I think it was when I was at that Manuel's defense in Lausanne, I was reminded of like a result more in the spirit of extremal combinatorics, like in the very standard way about sets that intersect, like how many sets can you have, blah, blah, blah. And so I was hoping that maybe this conjecture follows from a more abstract, a more simple statement about like vectors with a certain scalar product, okay? But since it's very close to these nice questions in extremal combinatorics, you know, I needed an expert in this, so I came up with like the theorem that I wanted to prove, but I had to ask some expert whether it makes sense. So I emailed Andre and asked him whether he thinks that this is true, and this was not known, and he was very excited about it, and we worked on it several months. And the actual theorem that we proved, and basically the other result is just an implication, more or less an implication of this, is the following. So this is a very clean statement without polytopes and anything else. It's the following. Suppose I give you sets of vectors in R to the D that both linearly span R to the D. I get back to this in a minute. Such that if you take the standard Euclidean scalar product with a vector from A and a vector from B, you always get 0 or 1. Okay, that doesn't make sense. So this D doesn't make sense. Okay, it's either 0 or 1 all the time. Okay, then you can show that, or that's what we do. We show that the product of the sizes of these two sets is bounded by that number, D plus 1 times 2 to the D. Okay. And you need that requirement. If one of the two sets doesn't span RD, you can choose the other set as the orthogonal complement. So that, I mean, then you can make arbitrarily large sets. So it seems that this is the right statement. If you have such a statement, you can also prove some other things. Oh yeah, I should say, I mean, this bound is tight. You can easily construct some very simple examples. You know, even this result has some implications. I mean, maybe like this corollary. I mean, this was known. It's not a big thing, but you know, for instance, I mean, this implies that if you take any undirected graph, you count the number of stable sets times you count the number of clicks, then this is bounded by this number, right? That's a simple implication. You just treat sets as 0, 1 vectors, and you have that thing. It's also tight. Okay, good. So results of this flavor exist in the field of standard extremal combinatorics, where they really talk about sets, or which is really about 0, 1 vectors. So here's, for instance, a result of Peter Frankel, which is even a generalization of our result, and I don't know how to prove that for vectors, which is you have two set systems, script A and script B, with a property that whenever you take a set of A and whenever you take a set of B, their intersection contains at most L elements. And for us, L is 1 in some sense, okay? Then again, you have a bound on the sizes of these two sets of the product, which is this, okay? And if you plug in L is equal to 1, then you get exactly our bound, okay? However, this is just for sets. So this is just for 0, 1 vectors. Now, in our case, we have arbitrary vectors, okay? So we have to work much more. And once you do this, I mean, how is it really related to the two-level polytope question? So what you do is the following. So you take your, I mean, suppose we have proven our result, right? Now what you do is take any two-level polytope. Now you can translate it without changing the property that it's two-level, right? So translate it so that the all zero vector becomes a vertex, right? And then you stare at the thing and you see what do we need. So, I mean, look at the inequalities, right? Look at the facets, right? I mean, suppose you have a facet, right? And it's not containing like the origin. Then if you write it in the form ax less or equal than b, the right-hand side has to be positive because the origin is feasible. So you can scale it so that it's ax less or equal than 1. Well, all the other vertices are on the other side. So it's ax greater or equal to 0 and so on also in the other cases. So what you can do is you can really, you can describe your polytope P in that form, right? So ax is between 0 and 1 for a certain set of vectors A, okay? So that's great. So this is your set A, and your set B is just the set of vertices, and then you're exactly in the business from the previous statement. Now you have to be, I mean, it doesn't follow black box because you don't want to count facets twice. I mean, like but I mean, if you know the proof of the first statement, you tweak it a little bit and then you have the exact bound. Otherwise you lose maybe a factor of 2. Okay, good. So let's focus on the actual, on this statement. How do you prove this? And I just give you a very rough idea. Okay, so here's the proof sketch. So what you do is you choose an appropriate vector from the set B. I won't tell you how to choose it. And then you just, I mean, once you have a vector B, you can partition your set A into those vectors that have a scalar product of 0 and those vectors that have a scalar product of 1. So that's what I call A1 and A0. Okay, good. So you have partitioned this. And now just for this talk, let's assume that these both sets are like d-1 dimensional, okay? So let's say in some sense they really are facets of the respective polytope, okay? Which is of course not true in general, and you cannot choose a vector B bar in that way, but let's hope you can do it, okay? So what do you do then? Well, I mean, basically you want to perform induction, okay? So now you have to think about how do I perform induction, okay? So you do induction exactly on the orthogonal complement of B bar. So that's what we call gamma, okay? And now you project your set B onto that set, okay? I mean, A0 and A1 are fine. They are already basically in these subspaces. Now you have to project B, but now you have to be a bit careful that, not too many points fall into the same image. But fortunately, if you're in that case, that won't happen, okay? I mean, not really. So the claim is that if you take that set B and you project it, most points will have a unique pre-image, except maybe that vector B, which was sent to 0, has a second pre-image, but that's fine. And yeah, the reason is somehow that so this is gamma. Okay, now suppose there are two vectors B0 and B1 that fall into the same image. Now just take any vector from A1. Okay, then these two vectors B0 and B1, they have scalar product 0 or 1 with that vector. Okay, and it turns out that they must have different scalar products with that vector A1, otherwise they're at the same point as the picture indicates. Okay. And so what we can say is, so maybe B0 is really the vector that has 0 inner product with A. Maybe B1 is really the guy that has inner product 1 with A. And now it turns out that no matter which vector from A1 you take, I mean, it's always the bottom one that has inner product 0 and always the top one that has inner product 1. I mean, yeah, it's easy to see that, okay? But then this means that B0 has inner product 0 with all points from A1. But now we use the fact that A1 has dimension d-1, which then implies that, well, I mean, this B0 is the all 0 vector. So only in that trivial case you have multiple pre-images, okay? I mean, just to give you a rough idea, okay? Good, but now you do simple counting and induction, okay? So what's the cardinality of A and B? Well, I mean, actually, this is an equal. Okay, so let's split up B into B without B bar and B bar. Okay, good. Now we heard that if you're distinct from B bars, if you don't project to that 0 point, right? I mean, the projection, there's a one-to-one map between the projection and these points here. So that's fine. And now I can split up A into A0 and A bar, nothing happens. And now the thing that you realize is that for these two guys here, you can apply induction. They I mean, after maybe translating one of the two sets, they satisfy the induction hypothesis. So you can really, you can apply induction here. And I mean, you have to be slightly careful because now these sets, again, they have to span R to the d-1 because this was one assumption, but that's fine. I mean, I'm currently assuming that I'm in a nice case. So you apply induction on these two guys. This guy, you have that simple estimate is at most 2 to the d. So this also holds for that setting. So you just write down all the estimates, you plug things together, and that's exactly the bound that you wanted to prove. So, okay, so this was very easy, right? But I cheated, right? I cheated. I made that assumption here, and this is what makes your life really hard. So this doesn't hold in general. I mean, yeah, this doesn't hold in general, and so if this doesn't hold in general, you have to be very careful and you have to count a lot. Then you really, I mean, this is really what you want to do. You want to project and you want to do induction, but you really have to think about like that you avoid multiple counting and so. But I mean, it's okay. It's okay for today. So that's everything I wanted to say. Thanks a lot for your attention.